Hey, Wade North, Mr. Jurgler here. We talked about chemical equilibrium. I also want to talk about physical equilibrium, and the biggest example of this is solubility. So let's take a look at the comparison between the two. In chemical equilibrium, the products that we're producing are always actually new products, right? We're going from a reactant and to a different substance, which is our product. And because of that, you often see color changes and things like that that we've seen in lab, for example. With physical equilibrium, it's a little bit different. We're not really changing the identity of the substance itself. So if you want to think of an example of this, think of like ice water. If you have a cup of ice water in a really well insulated container and you don't let any heat in or out, the ice water will reach an equilibrium with the solid ice and the liquid water. And it'll actually the ice will never completely melt and the water will never completely freeze. They'll always be in equilibrium with each other. The same is true of saturated salt solutions. So if you take table salt, for example, and dissolve as much as you can in it, eventually you get to the point where you can't dissolve anymore. And you'll have solids sitting at the bottom of the container, right? When that happens, you actually have an equilibrium between the solid salt and the aqueous salt. It's not the case that the reaction, which I put in quotes because it's really just the dissolving of the ions, that's not really stopping. It's not really stopping from dissolving. It's just the case that the ions are unforming, so to speak, and reforming the solid crystal at the same rate that you're dissolving them. So for every one that you lose, you're kind of capturing one more. And so you know how we've talked about in the past where soluble salts are either soluble or they're insoluble, right? And I've talked about the acronym SNAP to kind of remember which ones are soluble. Sodium nitrates, ammoniums, and potassium ions, right? Anything containing those we say are soluble. And that's true, they are soluble. And what we've said so far is that everything else is kind of insoluble, or we can assume that it's insoluble. And that's actually a complete lie. There's nothing that's completely insoluble. Every material dissolves to some degree. Now, most materials dissolve almost zero, but they still do dissolve somewhat. And a lot of salts, they are what we call slightly soluble, meaning that they dissolve a little bit, but hardly enough to be measured. A great simulation of this is found on the Phet website, Phet. I'll put a link in the description as well if you want to kind of click there and play around with it. Let me switch to looking at that. So here we have this simulation, and I'm going to start with table salt. Okay, so I'm going to add a little bit of table salt, and you'll notice that it dissociates right away, right? It breaks up into its ions. And let's just add a ton of ions in there. I'm going to add 200. And you'll notice that it's actually more than the water can handle, and so it reforms into its solid, right? And you guys may know this from experience. You can only dissolve so much salt in water. Now let's compare that to a slightly soluble salt. I'm going to use silver bromide as an example. We'll add some silver bromide to our solution, and a lot of it will dissolve and break up into ions, but some of it will stay together. And let's compare the two. Look at the concentration where this is saturated, and this is saturated because it won't dissolve anymore, right? Look at that concentration compared to the table salt concentration. This salt dissolves much less than table salt does. And so we need to have a way to kind of represent how this equilibrium works and where it lies in relation to products versus reactants, right? In this case, it's lying much further to the reactant side, which would be the solid, than to the product side, which is the ions. The Ksp is the solubility product constant. So it's a new kind of equilibrium that we're kind of adding on here, but it's really just the equilibrium of solubility. Every salt has its own Ksp. It's determined experimentally, so you'll find tables in the back of your textbook that kind of have a list of all these Ksps for all these different salts. And it's temperature dependent, just like any other equilibrium constant. In general, the higher the temperature, the more soluble salts are, but there are a few exceptions. There's a few that decrease in solubility as you heat them up. It's also affected by pH and what's called delta G, which is the amount of free energy. We'll talk more about this in the future when we get into thermodynamics, but we'll kind of abbreviate it and talk about it qualitatively here. In general, if the attraction forces between these ions in the solid is really strong in comparison to the attraction forces between the ions and the solvent, then it's going to be really insoluble. If the attraction forces between the solvent and the ions is stronger than the attraction forces between the ions themselves, then it's going to be more soluble. It's going to dissolve a lot more easily, right? And so that's related to how much entropy and enthalpy there is in the system, the amount of disorder, and so forth. But we don't need to get into that just yet. Let's look at a general equilibrium reaction of the dissolving of a salt, right? So you have some salt with a cation and an anion, and it's solid, and when you dissolve it, it forms its ions. So how would you write a K expression for this reaction? you would, like always, put products over reactants, right? K equals products over reactants. But in this case, and in any case where we're dissolving a salt, we're always starting with a solid, which is left out of the K expression, right? So then the Ksp essentially just becomes the product of the two ions in solution, right? Hence the name solubility product constant. Let's look at an example. So I specifically chose calcium phosphate because it has a lot of coefficients and subscripts. When you dissolve 1 mole of calcium phosphate, it actually produces 3 moles of calcium ions and 2 moles of phosphate ions, right? Go ahead and try and write the Ksp for this one. You should have written the calcium ion concentration to the third because of the coefficient here, and the phosphate ion concentration to the second because of its coefficient, right? And that would be equal to the Ksp. So the Ksp tells us basically how much of the solid is formed into ions when it dissolves. So if it's really small, then it's lower in solubility. If it's really high, then that means you can make a lot of ions, and the solubility is actually really high. Here's a sample table of a bunch of Ksp values. So this is breaking it up by type of salt. And notice that it's always at a specific temperature. And so if we look at like barium fluoride, for example, the Ksp is to the -5th. That's a lot more soluble than some others like bismuth sulfide that is incredibly insoluble. The way we describe this is what's called the molar solubility. The molar solubility is basically the number of moles that can dissolve in the water. And this is always going to be equal to X in an ice table. So let's look at an example. If the molar solubility of lead chloride is 1.6 times 10 to the -2nd, what's the ion concentration at equilibrium? Now I want to be clear, this is not the Ksp. The molar solubility is the number of moles that dissolves in a liter of water. That's different from the Ksp because the Ksp is the product of the two ion concentrations. And they're definitely related, but they're not the same thing. Let's start by writing our dissolving equation, and we can set up an ice table. Now you don't really need a full ice table, but I'm going to go through one anyways. We're always going to start with 0 concentration of our ions because we haven't dissolved anything yet. And then how much is this going to dissolve? Our molar solubility is 0.016, and so that's the amount of moles that's going to dissolve. It actually doesn't matter how much we start with, right? Because the amount of solid sitting at the bottom of the container is irrelevant. All we care about is the concentration of the ions that are formed, right? So if we're going to decrease this by 0.016, then we're going to increase the lead concentration by 0.016 as well. What should we put here? Remember to double it because we're producing twice as many chloride ions, right? And so at equilibrium, it doesn't matter what we have of the lead chloride solid, but it does matter what we have of the ions. So what would the Ksp be? It would be the product of those two concentrations, remembering to square the chloride concentration. So plug those numbers in and you would get 1.6 times 10 to the 5th. Now this is just coincidental that it's 1.6 for both the molar solubility and the Ksp. Those usually don't match. Let's look at one more example. If we're dissolving aluminum hydroxide, and we know that only this many moles of the aluminum hydroxide dissolves, let's figure out what the Ksp is. Again, set up like an ice table format, always starting with 0, and I'm going to use X this time to kind of keep track of what's happening. The solid is minus X, that's the molar solubility, and that's actually given, right? I know that that's 5.2 times 10 to the -9th. I'm going to leave everything as X, though, just kind of for kicks here, to kind of show how this works. So then I end up with aluminum concentration of X, and my hydroxide concentration is 3X. Now set that equal to my Ksp. We can plug in our X values. Remember to cube this one, and so we end up with 27X to the 4th. Now go ahead and plug in X and you end up with 2 times 10 to the -32nd, and then that's our Ksp. Now with comparing solubility, we have to take a few things into consideration. How many ions are these forming? Silver sulfide is going to form 3 ions, and nickel cyanide is also going to form 3 ions. And so the amount of moles of ions produced is going to be the same. And so in that case, we can actually just look at the Ksp values and take the larger one. The larger one is the more soluble one. Don't make the mistake of thinking that a larger number, 49, is bigger than 23. Negative 23 is bigger than negative 49. What about these 3? You actually can't compare these just by looking at it. You can compare the top and the bottom one because they are forming the same number of ions, but the middle one is only forming 2 ions. You're going to have fewer X's when you actually go to solve with the Ksp. Take the Ksp and solve for X. This is what you get. So it's actually the case that the barium fluoride is the most soluble and the barium carbonate is the least soluble. So just kind of in summary, if you're forming the same number of ions, you can just look at the Ksp. But if you're forming a different number of ions, you have to actually calculate what the molar solubility is, what the X is, in order to figure out which one is more soluble. If you have any questions on any of that, make sure you bring those to class. This is Mr. Euler signing off.